We are seeing the energy of stationary states, that is En equals minus RH into 1 by n square. What is RH? That is Rydberg constant. We have seen like hydrogen-like atoms, the other formula by using atomic number. That formula we have used here. Bohr model was also unable to explain spectrum atoms containing more than one electron. Hello everyone, this is Harshita Bhavasar from Vidhyaashram School of Excellence. Today we are starting up session 5 from the chapter Structure of Atom. We have discussed about the photoelectric effect and problems, dual matter of radiations and different types of spectrum. So these are the contents what we have discussed in the last class. Today we are going to discuss about Bohr's model of hydrogen atom and explanation of line spectrum of hydrogen and dual behavior of matter. So these are the contents we are discussing today, and first we shall explain what is Bohr's model for hydrogen atom. He is the Niels Bohr. What he has done means, so Niels Bohr, by applying quantum theory to Rutherford's atomic model, nuclear atomic model. So after applying so many observations, so many postulates he has came through. So what does that postulates means? The electrons revolve around the nucleus only in certain selected circular paths called orbits. Okay, what he told? The electrons revolve around the nucleus in a restricted circular path or selected circular path. Those circular path we'll call it as orbit. These orbits are associated with definite energies are called energy shells. So these are energy shells. What are the orbits? Will be connected with some amount of energy, definite energy. So those will be called as energy shells or energy levels or quantum levels. These are numbered as 1, 2, 3, 4, etc. from the nucleus. See, if it is, this is the nucleus part. We have to number from the nucleus. This is 1, this is 2, this is 3. Like that we have to number, and starting from the nucleus, and they are designated as KLMN. KLM, and remaining N we can go further also, etc. So as long as an electron remains in a particular orbit, it doesn't not lose or gain energy and its energy remains constant. Therefore, these orbits are called stationary states. See what he is telling means, whenever the electron doesn't move or remains in a particular orbit, it cannot lose energy or it cannot gain its energy. It will be in a stationary phase. That's why that whole level or orbit will call it as stationary states. Okay, once again repeating, the electrons revolve around the nucleus in a selected circular path. Those circular path will call it as orbits. These orbits will be having a definite energy. Those definite energy will call it as energy shells or energy levels, quantum levels. Okay, and these are numbered as 1, 2, 3, 4 and etc. And from the part of the nucleus only we have to start numbering, and they will be designated as KLMN. These are the main shells naming. As long as the electron will be in the same position or a place or in the same orbit, it doesn't lose or it cannot radiate any energy. Okay, it will be in a stationary phase or a constant phase. Those state will call it as stationary state. Okay, next we'll see the Bohr's model of hydrogen atom completely in a discussion manner. When transition occurs between two stationary states that differs in energy, the frequency of the radiation absorbed or emitted can be calculated as. See, here transition, what do you mean by transition? We have already seen that this is nucleus, this is one orbit. Okay, see here if it is having one electron, hydrogen will be having one electron. So if it is going to or jumping to outermost electron, outermost shell, this energy level to moving for another highermost energy level, the moving is known as transition. We'll call it as transition. Occurs between two stationary states. This is one stationary state and this is one stationary state. The electron is jumping from one stationary state to another stationary state. So, it will be differing energy. Yes, here the stationary state will be having some energy level, but this stationary state will be having different energy level compared to the first energy level. And also the frequency of radiation. See, the electron is jumping from first to highermost level, okay? And it cannot stay there because the stability is not there. So, it will move back to its original state. While moving back, it will be emit some radiations. Those radiations will be having the frequency, right? So, the frequency will be how it has been calculated, we are seeing now. This is the frequency of radiation, what it has been emitted. So, delta E by H. How delta E? That is E2 minus E1 by H. This is H is Planck's constant. E2 means the energy of the higher state. Higher state means excited level. See, it has been excited here. Okay. This is the E2 level energy. Okay. This is lower energy level, means the ground state or the original state of that electron. Ground state. This is E2, this is E1. Okay. Those energy we have taken here E2 minus E1, this is what? Planck's constant. Once again we are telling what are the terms here. We have used frequency of radiation, nu means frequency of radiation, H means Planck's constant, E1 is energy of lower energy state, E2 energy of higher energy state. Okay. Next, an electron can move only in those orbits for which its angular momentum is an integral multiple of h by 2 pi. Okay, what they are telling? The electron, whichever can move, it will be or it will move in the direction or it will move in the orbit which has angular momentum. Means, see, one electron is moving in one angle, another electron will move in another angle. The angles will be different. Momentum means velocity, right? So, the angular momentum with integral multiple. Integral multiple means it will be in a integer having so many with having multiples. So, that is h by 2 pi. Here the angular momentum will be h by 2 pi. Here only the electron will move. In other words, angular velocity of electron in an atom is quantized. What do you mean by quantized? Electron will be or the velocity will be having here 1 to 2, 1 or 3 like that. In between 1 to 2 in a fraction it cannot be there. So, see here n equals 1, 2, 3. In between 1 and 2 it will be not there. 2 and 3 it will be not there. In a definite number or a whole number. Okay. See here the equation, mass of electron and velocity and radius equals n h by 2 pi. N is here integer and h by 2 pi is the angular momentum. So, these are the first two postulates. And next, stationary states for electron are numbered in terms of principal quantum number. Okay. How the stationary states have been named means about the principal quantum number you will see in the next session. So, now the stationary states of the electron will be designated from the principal quantum number, that is n equals 1, 2, 3. 1 means first orbit, second means second orbit. We should know that from the nucleus we are starting the numbering. Okay. 3 means third orbit of the whole electron system. Next, for hydrogen atom, the radii of the stationary state is expressed as Rn equals n to the power n square into A naught. Okay. A naught is having a constant, that is 52.9 pm. For the hydrogen atom, it is having this much, 52.9. For this equation, we can substitute as a hydrogen atom, that is Rn equals n square means hydrogen will be having only one electron, that is 1 square into A naught how much? 52.9. We will get Rn equals 52.9. So, since we get the 52.9 itself, we'll call this one as Bohr radii also. Okay. Next, energy of stationary state. We are seeing the energy of stationary states, that is En equals minus RH into 1 by n square. What is RH? That is Rydberg constant. 2.18 into 10 to the power of minus 18 joules. What is n? The number of the orbit, first, second or third, or it may be continued. So, we are substituting this Rydberg constant to that equation, that is En equals minus 2.18 into 10 to the power of minus 18 into 1 by n square. We can substitute this n as 1, 2, 3, anything. Next, for ions containing only one electron, for example helium, lithium, beryllium, we will follow this equation. They are telling indirectly like hydrogen-like atoms. Hydrogen will be having only one electron. Here is also, these are the atoms like hydrogen. Means helium. Helium also having one electron. Helium, this is plus. Helium plus electron means usually helium will be having 2 electrons. Okay. So, helium plus means it will lose one electron containing only one electron. Lithium will be having 3 electrons. After losing the 2 electrons, it will be having only 1 electron. Means it will be the whole hydrogen-like atom. First energy we'll see equals minus 2.18 into 10 to the power of minus 18 into z square by n square. Z square means, this z square means atomic number. This n square means we know that the number of orbit. Okay, the radius 52.9 into n square by z pm, where z is atomic number, n equals 1, 2 or 3. Next, the explanation of line spectra of hydrogen. We have seen in the previous session about line spectra and various kinds of spectrum. Now we are having the complete explanation of the hydrogen spectrum. According to Bohr's postulate, radiation is observed if the electron moves from the lower orbit to the higher orbit, whereas the radiation is emitted if the electron moves from the higher orbit to lower orbit. The energy of difference between the two stationary states is given by, see, already I have written, this is the nucleus. These are the orbits. This is an electron. It is moving towards the higher energy level, and it has higher, moving from lower to higher energy means it has been excited. Okay. So, where it has been started jumping, that we will call it as EI. Where it has been jumped, that we will call it as EF. If it is coming back like to original state, then we will call it this energy as EI, this energy as EF. Okay. EI means, I means initial, F means final. E means energy, we know that. See, delta E means the difference between E2 minus E1. Okay. EF minus EI, the final energy and the initial energy. Okay. Delta E equals minus RH by N F square minus RH by Ni square. This is the energy equation what we get from the Bohr's atomic model. Here they have substituted Ni and Nf stand for initial orbit and final orbit, where delta E equals RH. Here they have given, they have taken common RH outside. RH equals 1 by Ni square minus 1 by Nf square. This is the RH constant, like Rydberg constant. We have substituted here, that is 2.18 into 10 to the power of minus 18 joules into 1 by Ni square minus 1 by Nf square. These things will not touch now, only we have substituted the Rydberg constant. Okay. These Ni and Nf will be keep on changing about the electron. Next, in terms of frequency, nu equals frequency of, for absorption and emission of the photon can be given by. The frequency, whatever the absorption or giving out the emission of photon will be known from the radiation of frequency. Okay. So here delta E by H, how they have taken? Nu equals delta E, that is E2 minus E1. See here, the frequency for absorption and emission of the photon can be given by, how the radiation for the frequency we have given means, we know E equals H nu. This is the common formula, and we are substituting that nu we have taken out because we have to find out what is the frequency. So nu we have taken out delta E by H. Okay. Delta E means this is the constant where we have used, and see here delta E means RH equals 1 by Ni square minus 1 by Nf square. This is delta E. This H, what we have taken, that is Planck's constant. What is the Planck's constant? Or first what we are seeing here, this is Rydberg constant, 2.18 into 10 to the power of minus 18 joules. That is Rydberg constant here we have substituted, and this is 6.626 into 10 to the power of minus 34 joules. This is the Planck's constant, and we have substituted here. As I told already, these energy levels we will not touch yet. Okay. And by dividing these things, we will get 3.29 into 10 to the power of 15. Okay. And this is the nu. And in terms of, this will be in hertz. Frequency will be seen in hertz. In terms of wave number, we are seeing here how it can be wave number here. See, wave number means nu by C. They have taken, they have given like this, right? C equals nu lambda. This is the common equation. We are taking out this one. 1 by lambda equals C nu. C by nu, this one. C by nu. 1 by lambda or 1 by wavelength means reciprocal means wave number, that is C by nu. Okay. This wave number have become from this, that is nu by C, and again RH, this is Rydberg constant, and divided by Planck's constant into velocity. This is the common equation where 1 by Ni square minus 1 by Nf square. See here, nu what we got, that is 3.29 into 10 to the power of 15 per second. What this is? 3 into 10 to the power of 8 meter per second. What is this? This is C, velocity. This much what we have taken from the frequency, here we have substituted. Only C we need to find. So here we have written. After all everything substituted, we will get 1.0967 into 10 to the power of 7 into 1 by Ni square minus 1 by Nf square per meter. This constant we have seen in the hydrogen spectrum also. There are two cases. In case of absorption spectrum, if Nf is greater than Ni, if this is the case and the term in the parenthesis is positive, whatever the term we will get, it will be always in positive, and energy is absorbed. At this stage, the energy will be absorbed and the term will be in a positive. In the other hand, if the case of emission, that time we will see the case, that is Ni is greater than Nf, that is initial will be greater than final orbit. That time energy is always negative, and whatever the energy we will see, it will be released or emitted. We will see some of the problems here. What are the frequency and wavelength of a photon emitted during a transition from n equals 5 state to the n equals 2 state in the hydrogen atom? Here we need to find out the frequency and the wavelength of a photon, and they have given n5, that is energy level, and n2 state. Solution will see, Ni is the initial level, that is 5th, Nf is the final level, that is 2. This transition, here the transition have been taken place, gives rise to a spectral line in the visible region. The overall whatever the spectral region will be seen, that will be in the visible region of the Balmer series. From the equation, we know this equation delta E equals RH, that is Rydberg constant, into 1 by Ni square minus Nf square. This is the Rydberg constant, 1 by Ni square minus 1 by Nf square. Okay. Here we have taken one side, Ni is 5, we have taken, Nf is 2, we have taken. After all, everything substituted, we will get minus 4.58 into 10 to the power of minus 19 joules. This is the energy what we have got. Okay. You know the transition, how the initial level to final level we will see, how the transition will take place, how it will be emitted, how it will be absorbed. Based on those terms, they have given this problem. And again, we will see the emission energy in that. That is an emission energy because it is in minus sign. We already know two cases. If it is initial is greater than final, we will get the negative sign, that is emission energy. The frequency of photon taking energy in the terms of magnitude is given by frequency, that is nu equals delta E by H. What is the delta E? We got in the previously 4.58 into 10 to the power of minus 19 joules. By this is Planck's constant, it is a constant. After that we will get 6.91 into 10 to the power of 14 hertz. Frequency always we have to written in terms of hertz. Later they told we have to find out wavelength also. Wavelength C by nu. Okay. This is 3 into 10 to the power of 8, constant for velocity of light, by whatever we got here frequency, those things we have substituted here, we will get 434 nanometer. Wavelength we will should write in terms of nanometer. Next problem, calculate the energy associated with the first orbit of He plus, that is helium. What is the radius of the orbit? For radius, we have one formula. Also, we have to calculate the energy. So, first we have taken the energy minus 2.18 into 10 to the power of minus 18. This is the constant by n square, z square by n square. We have seen like hydrogen like atoms, the other formula by using atomic number. That formula we have used here. Okay. For He plus n equals 1, z equals 2. That is, it will be in first orbit, atomic number is 2. After substituting those things into the formula, we will get minus 8.72 into 10 to the power of minus 18 joules. The radius of the orbit is given by equation. Now we are finding the proper radius, that is 52.9 into n square by z, picometer. These things we are converting into nanometer. So, 0.0529 into n square by z. Since n equals 1 and z equals 2, again we have to substitute here. We will get 0.02645 nanometer. Okay. Again we have to be write in nanometer terms itself. Next, limitations of Bohr's model. After all these things, some of the limitations will be present in the Bohr's model. What are those limitations? We'll see now. Bohr's model failed to account the finer details of the hydrogen spectrum. Means in the spectrum, see here, in the spectrum we'll see like these lines. Within these lines, small finer lines will be present. Those finer lines he could not explain about its details. So, first limitation he failed in that. Instant splitting of a line in the spectrum into two closely spaced lines. That's what I told now. This is the one line of spectrum. Into that many spectral lines, many finer spectral lines will be present close to one another. Those details he could not give, or he could not account it with complete details. This is the first limitation of Bohr. Bohr model was also unable to explain spectrum atoms containing more than one electron. See, why he has taken always hydrogen? It contains only one electron. More than one electron means he could not explain its whole theory into that electron. Hydrogen he took and he explained. He plus, helium plus what he took, that is also he explained because containing one electron. Again lithium also, when it is containing one electron, he explained. Like that, only containing one electron only he explained. More than one electron, he could not explain his whole theory. Bohr theory was unable to explain Zeeman effect. What do you mean by Zeeman effect? That is splitting of spectral line in the presence of magnetic effect. Okay, whatever the splitting in the hydrogen spectrum will be seen, in the presence of magnetic field, he could not explain that. That effect will call it as Zeeman effect. And he could not explain the Stark effect also, the splitting of the spectral line in the presence of electrical field. Okay. Bohr's model could not explain the ability of atoms to form molecules by chemical bonds. How the molecules will be forming through chemical bonds, that also he could not explain. Whatever he could not explain, that is finer details of spectral line, and also more than elements containing more than one electron, he could not explain. Zeeman effect and Stark effect also he could not explain. Bohr model could not explain the ability of atoms to form molecules by chemical bonds. How the atoms will form molecules by chemical bonds, these are the things he could not completely explain. So his theory was failed. After this failure, the Bohr's model, some of the experiments by using Planck's quantum theory, they told matter will be having dual nature. What do you mean by dual nature of matter? Matter will be acting as a wave and also particle. So, dual behavior of matter also existed here. De Broglie proposed that the matter exhibits dual behavior, that is, matter shows both particle and wave nature. What we have seen before, the wave-like and particle-like in the presence of light, we are same in the radiation, we are same telling here that matter is also containing dual character, behavior, that is matter-like and wave nature. How they have been explained that one? By the help of Planck's quantum theory, they told E equals h nu. Okay, according to Einstein's equation, E equals mc square. By equating both the Planck's quantum theory and Einstein's equation, they told h nu equals mc square. H nu by lambda he got. Here nu equals c by lambda. Again they will get c1, one c will be cancelled. See here, this is the overall equation for the de Broglie's equation, that is lambda equals h by mv equals h by p. What is this mv? Mass into velocity is momentum, that he has explained. See, where lambda is wavelength, h is Planck's constant, p is momentum, h is Planck's constant, and this is mass into velocity. Mass into velocity is equal to momentum. Okay, that is designated by p. This is the de Broglie's equation. Another one, Heisenberg's uncertainty principle. What he told? It is impossible to determine simultaneously the exact position and the exact momentum of an electron or a velocity of an electron. Okay, he told when the electron is moving around the nucleus, it will be in a moving position. What he told means, at the moving of electron, he could not predict the exact position and the exact velocity simultaneously. Okay, for that, delta x into delta p is equal to h by pi. Delta x means uncertainty in position, delta p means uncertainty in momentum or velocity, h by pi. Okay, we can write it as delta x into mvx, mv mass into velocity equals p, that is equal to h by 4 pi, where delta x is uncertainty in position, delta p is uncertainty in momentum, and delta v is velocity. He told again that he could not explain the exact position and exact velocity simultaneously of an electron. Okay. What is the significance of uncertainty principle? Means it rules out the existence of definite path or trajectories of electrons and other similar particles. See, Rutherford told, that is, orbits are present around the nucleus, but he told orbits are not present, and also existence of The paths are not correct, he told like that. The effect of Heisenberg uncertainty principle is significant only for motion of microscopic objects and is negligible for the macroscopic objects. Whatever he told the uncertainty things, it will be applicable only for microscopic things, not for macroscopic objects. Next, reasons for the failure of the Bohr model. What are the reasons? In Bohr model, electron is regarded as a charged particle moving in a well-defined circular orbit. He told it will be in a well-defined circular orbit. It cannot show as a truth. The wave character of the electron is not considered in Bohr model. The wave character of the radiation he could not accounted in his theory. So, these are the two reasons of the failure of Bohr's model. Next, we will see 2 to 3 problems here. What will be the wavelength of a ball of mass 0.1 kg moving with a velocity of 10 meter per second? Here we have to find out wavelength. Okay. According to de Broglie equation, we know that is delta equals h by mv, that is equal to h by p. H is Planck's constant. Here we have written the constant. M into v, they have given mass of 0.1 kg, velocity of 10 meter per second. After all calculating this, we will get 6.626 into 10 to the power of minus 34 meter. Okay. Next, a microscope using suitable photons is employed to locate an electron in an atom within a distance of 0.1 angstrom. What is the uncertainty involved in the measurement of its velocity? Here the uncertainty means Heisenberg uncertainty principle we have to use. What does it mean? Delta x into delta p equals h by 4 pi, or delta x into delta v, delta m into v equal to h by 4 pi. We have to find out the velocity we have taken outside. So, it will become h by 4 pi into delta x into mass. We know the Planck's constant, we have written here. 4 pi, pi means 3.14, this is the pi value. 0.1 they have given into 10 to the power of minus 10, they have given in the angstrom. So, we have to substitute 10 into 10 to the power of minus 10 meters into 9.11 into 10 to the power of minus 31. Okay. All substituting this, we will get 0.579 into 10 to the power of 7. They are changing the position, the decimal. So, it will be decreased, that is 10.6. The overall value is 5.79 into 10 to the power of 6 meter per second. These are the things what we have discussed today about uncertainties and also the failures, overall the things of Bohr's atomic model. Okay. Now, in the next class, quantum mechanical model of atom, quantum numbers, regarding that we will use some problems. I hope you have understood what I have discussed today. So, thank you everyone. We will see in the next session.